Next up, I am so happy to introduce Jose Hernandez and Michael Haag. I had the opportunity to see their presentation earlier this week, and they're going to be talking about a very important topic, Cobalt Strike. In addition to talking about Cobalt Strike, they are going to be releasing a tool as well. And with the name like ZoidbergStrike, how can you go wrong with that? I think one of the things that I love best about this community is I feel like sometimes we are all, standing on the shoulders of giants, and Jose and Michael definitely fit that bill. They have taken the time to do the research, to write a tool, and here they are today to present on that and share it with us, which I think is, what this conference stands for. Absolutely. So I will turn the floor over to you, Jose and Michael, and I'm excited to see your presentation today.
Happy Thursday, everyone. So let's get started. So super happy to be here with Mike. We're going to be talking today about mining the shadows with ZoidbergStrike, a scanner for Cobalt Strike. Quick agenda. We're going to cover a little bit of like what Cobalt Strike is and why do we hunt it. Then we'll dig into ways you can find a team server in the wild. Like, what are different techniques to find team servers in the wild? Then we'll jump into a demo for this tool. And thank you, Mary, by the way, for the kind intro. I totally jumped over that out of nervousness, but appreciate that. But we'll be demoing this tool, right, that we wrote to find team servers in the wild. Then digging into the architecture of the tool. And finally, Mike is going to walk us through, like, how do you use the data that the tool generates, and in general, how do you just detect Cobalt Strike in general, but specifically around the data that we're collecting. Yeah, I hope you enjoy this. So let's just dig right into it.
Awesome, thank you, appreciate it. Yeah, so what is Cobalt Strike? I hope and assume most everyone here has heard of it at least once. It is a adversary simulation tool, red team operations tool or product. And it's turned into the de facto standard for pretty much every adversary out there now. Nearly every breach seems to have Cobalt Strike around it. Why is it so popular? Well, it's something that was just locked up where you had to purchase it, now is cracked and leaked everywhere. Every version seems to be coming out. And then, most recently with like Conti leaks, and we're able to kind of view into like how these actors are using it. And, no longer is it red team, but it's also, obviously tracked by MITRE, and you can see on the right all the different groups that also use it. And it's notoriously never out of the news at this point. I could just do more Googles and find nearly every article that could just fill up this slide. I just grabbed a couple of the quick ones. And these are already out of date, right? But probably the most prominent breaches that have used Cobalt are now related to like Nobelium Group, SolarWinds, Colonial Pipeline, and every ransomware group out there today. When we started digging into Cobalt Strike more, and in ways to find Cobalt Strike team servers on the internet, a tool was released from, I think it was Wade Hickey, I think at the time was with Rapid7, and it was a tool called Grab Beacon Config, and it's an Nmap NSE script. And the idea of it was to, find IPs and scan them and pull a beacon config from there. And so when we were working on this project, we were debating on like the approach to go after this. We could get in the business of scanning the entire internet and, using Nmap, mass scan, whatever it may be, and just scan everything and, catch stuff. Or use third-party tools that scan the internet already. So something that most everyone's probably aware of is like Shodan or Security Trails, maybe some ZoomEye. So that's what brought us to this. And then I'll let Jose take these ones.
Yeah, so there's different approaches, really. Like these two different approaches, there's different pros and cons to them, right? If you're scanning the whole internet, well, the cool thing is you're finding real active stuff out there. Like it's live, right? You have the freshest data set. It's obviously not relying on any third party. Ideally, if you're scanning using your own tooling, your own infrastructure, and as a result of that, you can probably tailor it to collect whatever you want, since you're not, again, dependent necessarily on the structure of the data that internet scanner providers provide through their API. But there's a few cons to this. The first one is you're scanning the internet. Now you're in the business of scanning the internet, which is a hard problem at scale. Finding VPS providers allow you to do this, e.g. bulletproof hosts. Wiring up a collection of tools to do this, again, at scale, it's nothing trivial, again, if anybody's ever digged into it. And it also tends to be a slower process than just making a query against one of these providers, right? By far. Now, using third parties to scan the internet also has some pros and cons to it. The obvious pro is, well, everything from the last slide that's a con is a pro here, right? But beyond that, you also have confirmed active data from the last month, right? Like these scanners typically, again, most of the Shoda and security trolls, they're confirming the results they're putting on their API, right? And the other beauty of that is you're getting now enriched data out of the box. Like you're gonna have ideally things like who is information there, DNS information, likely like information about the SSL certificates if there's a web server already embedded. You don't have to like wire this stuff up yourself, right? One obvious con is, well, now this costs money. You probably argue that doing it yourself also costs money, but here it's an obvious hard cost to it, which is the subscription to a service provider. And you're kind of at the mercy of the last time that provider scanned the internet, which time may vary, and depending on your licensing, you may be able to get some data faster than others, but you're relying on them regardless in the last time scan. And because of that, you also may end up with like finding in your results sets inactive team servers, or maybe a team server that went up a month ago and then all of a sudden got shut down a week later, and it still shows up in the scan because that scan is a month old, right? So that ends up being inaccurate results, right? If you're using these for searching. So
we more or less broke it into like 4 methods to go for finding team servers on the internet. So using the services route, most all of them provide the SSL JARMs, and there's been a lot of public data that's been released on, just different JARMs that have been related to Cobalt Strike Team Servers. And this goes back like probably a few years now, with like Risk IQ releasing one of the first blogs on, finding team servers and whatnot with their product. So there's lots of JARMs that we can use. And then mixing it with like ports. Not every port needs to be scanned. There might be very specific ones, and that's what we target. And then looking at like HTTP responses, Michael Kasquara and Pavel released a tool recently too. But one of their like Shodan dorks is looking at the responses. So like the HTTP 1 404 not found and content length 0. And then when you're looking at this data, it's really quick and easy. Once you scan or find a grouping of team servers, malicious ones, or red teams potentially, you can pivot on ASNs or by providers from that point. So maybe it's worth going after the whole ASN. You could scan all of it, or just start looking for the different JARMs out of that from those third-party services and the data you get. And then all these combined, right, you can start to filter down, reduce a lot of the noise, and really start to pick out the true team servers.
Yeah, so I guess the big question here is like, so you scan the internet using one of these third-party scanners, you got a result. The next big question is, how do you coerce one of these team servers to give you a beacon, right? And Mike affectionately titled this slide, how I've learned to become a snake charmer using NSC scripts. But Wade Hickey, we found, had open sourced this project called, basically it was a NSC script to rip a beacon from an already running team server, for lack of a better word. This script was called grab beacon config. And in short, this is what the beacon did under the hood was it would try to fuzz or guess the URL the team server would generate automatically to host this beacon on for HTTP and HTTPS beacons. And it then would, once it found a matching URL, if it did, given a result, it would then hash that response. And as a result of that, after grabbing the hash, it will also analyze, and from that response, pull away different configs parameter that Mike will get a little bit more into later, but basically the config parameters of the malleable profiles or the profile for that beacon, and return all that back into mmap, right? Since this is an NSE script as a JSON structure. So at the heart of this entire thing, this is it, right? This is how we are pulling beacon configs out of like known team servers. This is an example of what that data that grab beacon pulls back. It's basically every configurable parameter, like I mentioned in malleable profiles. So you get things like what is the jitter, what is the callback method, what are the spawn twos. We'll get into more of the details of this data in a second, but I just want to give you a quick idea of what is the kind of data this pulls back, right? So actually, without further ado, let me show you the tool we build that does exactly this. It scans the internet, or uses the data from these internet scanner providers, then verifies the results back, pulls down a beacon, and well, I'll stop talking about it. Let me show you actually. It's much easier, better. So first things first, installing the tool is super straightforward. If you've installed any Python application in the past, go to GitHub. We'll paste the repo at the end of the talk in the Slack channel. But go to the GitHub, git clone. Basically, it requires virtual environment and Python 3.18. It's as simple as git cloning, installing virtual environment, and then installing dependencies right afterwards. So that's what I'm doing right here. To install, and by the way, we use virtual, so we don't pollute your local system's Python with our dependencies for this tool. So yeah, this is what we're doing in this case. The tool is very easily configurable. It has a lot of the stuff already preset out of the box for you. So the configuration is under this like a conf.example file that ships with it. It stores all the results in this file called results.json. And again, by default, it already ships with the NSE script embedded. And we have the searches YAML file here. We'll get to it in a second, but the next important bits here are the different API tokens for these internet scanners. You don't have to have all three. One is perfect. It'll work through different ones. So if you copy and paste that config file example under the conf, just regular conf here, put your API tokens in there, you should be ready almost to go. So quick view here on the search file. This is a curated set of, for lack of a better, dorks that actually Mike has curated to find Cobalt Strike servers from different analysis we've done. But anyway, we'll get into how some of these actually work in a second. The important part is this is where they live. If you ever want to add your own or customize one, you can just add it in here in simple YAML config file. So once we run the tool, we're ready to go. We've already configured. You immediately see the tool will kick off and it'll start gathering IPs from the different searches you provided it, right? So for example, the first search returned here 383 results. And so it paginates through all the results, stores them. The next search, 38, the following 595, right? So it's running these searches across its internet scanner providers, and it's essentially collecting the IPs and ports from potentially Cobalt Strike Team servers out there, but we don't know yet, right? So in total, it collected 1,200 potential servers out there, and then it starts using essentially this grab beacon config from mmap under the hood to determine whether there's actually a server there, it's alive, and if it's actually a team server. And if it is a team server, then it's going to try to, again, coerce out its config or reduce. That's what we're calling here, reduce its config. And so they'll run through that 1,200 that we just saw. And by the way, I recorded this about 4 days ago, so this is pretty fresh data. Some of them, again, like I mentioned, may not be alive. We may not be able to reduce, but in total, for example, out of this 1,200, it returned 306 beacons or beacon configs. If you want to we can take a quick look here at what a config actually looks like. And like I mentioned earlier, this is JSON structure. We are kind of curating this structure as part of the tool. And the reason we're doing this is to make it very easy to go and ingest in an analytics tool. But can you see here like things like what the actual command under the hood we ran for mmap for troubleshooting purposes if you want to run this on your own. But more importantly, the beacon information, right? Like what IP it was on, what port, what the watermarks, what are the C2 servers is configured to point to, on what are the spawn twos when it infects a system that is going to, or process is going to spawn into, so on and so forth, right? And so this is, again, since this is already in a nice JSON structure, you can easily bring it into any analytics engine, Elk, Splunk in this case, and it is, again, very easy to visualize. Splunk eats JSON natively, so does Elk, or any, actually, most analytics tool out there. And immediately you can start getting some like awesome ideas, like some awesome patterns of like what are the most common beacons and how they're configured out there in the wild at the moment. At least the ones that are publicly exposed. Like, hey, what are the top spawn twos, for example? Anyway, I don't want to steal any thunder, but Mike is really going to deep dive into what some of these mean and why are they important. But again, we wrote this in JSON to make it very easy to bring it into analytics provider and then be able to visualize and run analytics on. Again, here's a quick example of a dashboard we built for ourselves to get a quick glance of like, what are the different DNS idols that were out there configured at any given time? What are the different spawn tools, so on and so forth. So what do we just see at a really high level? And just to give you an architecture of the entire tool, there's two modes of operations for the tool. One is you provided API tokens and it's going to go scan the internet using these internet service providers. Two is you just give it a new line delimited IP list, and it'll just try to rip the beacons from those IP lists. And again, if you wanted to do some manual testing, we added this mode. We found it to be super convenient as a result. But if you're providing it, if you're not providing an IP list, or read the searches from the search YAML, and then iterate through every provided, every configured internet scanner provider, and then pass those results into the mmap scan function, which will then grab the beacon information and write the results into a JSON file. It's a very, very simplistic workflow, I think, in many ways. If you're passing an IP list, it's just going to skip the whole internet scanner provider piece, just run, grab beacon, and then write the result. Like, again, this curated set of JSONs back into this results file. This is the, in a nutshell, the guts and glory of the tool. And again, like I mentioned, makes it very easy to then analyze what's out there, right? So I'll pass it back into Michael so he can talk a little bit about how we can actually use this data.
Awesome. Thank you, Jose. Yeah, so from here, I broke this into 3 sections, mostly just so that we kind of have like a little bit of, way to get through all this. Starting with simulate. Now I say simulate, that's if you have Cobalt Strike, and or you can go and capture malleable profiles, and we'll talk about that. Then we'll review this data for patterns and look at the behaviors of it. What can we build from here, and then begin generating content. So to begin with it, we have to understand what malleable profiles are. And I know we kind of touched on it, what it looks like when we pull a beacon config. But in this case, let's take a little quick step back. A malleable profile is like the configuration piece for Cobalt Strike. This is loaded up as you start a team server, and it has all the configurations. You saw all the post-exploitation stuff that we pull from the config. All of that can be modified. You can change the user agent, DNS, all the different settings, how they post, where they post to, what it looks like. And the idea of Cobalt Strike is to emulate normal behavior and or emulate actual adversaries and what they do in your environment, so you can see if you can detect it. So the quick references you can generate or go to is like the malleable C2 on cobaltstrikes.com's website. If you want to see probably some of the better profiles that are out there, I would recommend looking at Threat Express. They have a really good jQuery profile that's probably the most used. And they update it per version that comes out of Cobalt Strike, so you're able to play with the latest. And so when we're building content, most everyone should be able to look at it from either the endpoint or network. What products in your stack provide that visibility? And if you don't have the product or or the data itself, we have also generated this data in our environment, and that's at our 2 links at the bottom, which lead to our Splunk attack data repository. We have 2 of them in there. One of them is very heavy focused on network, but there's also a pretty big endpoint piece as well. So, and then the triangle just covers what we can get from malleable profiles. You can get named pipes, you can get the spawn to, all the post exploitation, different settings that are configured, down to DNS and URL and URI patterns and whatnot as well. So then moving on, inside of the profile itself, it's very simple looking. When you get these from GitHub, you can like quickly, easily just go right to the key parts that at least I look for, which is like the spawn to, named pipes, and some other settings like DNS idle and whatnot. But these are all easily configurable. Quick note on spawn twos, we'll call this out in a minute, but like you can have more than just that process name. You can put, it's up to 63 characters, so you can add like command line arguments in there. It's not that common, but it is available. And all of my notes that I'm covering here are on my repo there on that link, mhaggis notes. I'll put that in our Slack channel if you want to follow along, or just have for a reference later on. And here we go. And again, Threat Express, their jQuery profiles are going to be your best bet if you really want to like dig in and see all the amounts of configuration that's possible. So once you kind of get that very quick, brief understanding of malleable profiles and how they look and whatnot, let's look at some of the default settings that we get from profiles and or the beacon configs that we pull out of these servers. So real quick on the network side, again, all of these are static values in the base team server config. So DNS idle set to 0, which will cover what that means and what it looks like. Getting a request or posting a request over DNS, like for A records or quad A or TXT, have very specific patterns. And these are all, again, very heavily default. They're rarely changed. And I'll show you some of this data as well. And then the name pipes. Everybody, I think, has talked about the default pipes from Cobalt Strike at this point. Their patterns are pretty simple. It's on the Cobalt Strike blog. There's all these other blogs that cover it as well. And then the default spawn to has always been run DLL32.exe. There is no command line arguments for that. So we'll talk about that here in a second on spawn twos. I focused on DNS because it does stand out a lot more. Again, HTTP, we can definitely go after it. And there's a really good blog by the DFIR report where they dig into, it's a defender's guide on Cobalt Strike, where they dig into all the different settings. And they show a giant list of emerging threats signatures for network. And you can see that ET had literally went to each profile and started adding those. The issue is a lot of these profiles are meant to blend in with normal traffic. So there's an Amazon profile. That means the traffic's going to look like someone browsing Amazon.com. So I don't focus too much on the HTTP side. So then moving forward, this is what we gathered from scanning the internet, scanning with our services and ZoidbergStrike. We pulled out all of these. This is basically almost like a rehash of the dashboard. You can see the commonalities of the spawn twos in the bottom right. You can see that run DLL32 is the most common one that you will find out there. You have a pretty high chance that you'll run against run DLL32 compared to some other system 32 binary. And most recently, Red Canary, Shane and I, we wrote a blog on how we more or less baselined system 32 so that we could have better detection and coverage for all these type of behaviors. That's the link to the blog right there. And it's really detailed on how we did it and everything. DNS idle, we're gonna dive into, and then watermarks we'll jump into more here as well, and about how those are used and why that's important. So then what I did, and this is found on my notes page, the other way that I gather intel or just more data and understanding of what's used, you can scan, you can get all the services on the internet, pull the beacon configs, analyze those. The other thing that I do is I go and I scan GitHub because everybody puts their malleable profiles on GitHub. And so I have a very simple script. You just pop your API in, run some simple keywords, and then you end up with all kinds of fun stuff. And this has been detailed in maybe 1 or 2 blogs. I think I may have posted something as well. But you can see there's some other spawn twos that are popular out there, like Waterfall. You can see that service host has, a little bit of a command line, and then as you can, GP update and whatnot. And then on the right, you got some very standard pipes over here. There's not a lot of deviation from this. I find that a lot of teams or adversaries or whatever it may be that's putting these on Git, they're just copying and pasting from one profile and just modifying a few settings here and there, or no settings at all, and they're all very default. All right, now generating content, more or less, it's pretty simple. Once you have all this data, whether your scan data or your malleable profiles from GitHub, but it's simple enough to look at these processes. And so spawn2 is the process that is spawned and it injects into it, and that's where like all your post exploitation sort of happens at that point. It's most commonly found like in an EDR product as run DLL32 being spawned. There's no command line arguments, and there's generally always a network connection. It's a very high signal. And another part, if you get the paths and all that data as well, you'll see that sometimes it spawns from sysnative, or if it's an older box, it'll hit syswhile64. Those are hard-coded in malleable profiles. Red teams, actors, they don't change sysnative to system32. The idea is that sysnative will always be called, and so that's why they always leave it in there. And again, I referenced the DEFR report. Their defender's guide is very detailed on a lot of this as well and what they see. And in generating this data, if you're simulating it in like a lab environment, I recommend hunting naked. And that basically just means having a very wide open sysmon config so you can gather all this data and just see and understand how it all works. And that would obviously include named pipes and all the cross-process events and whatnot as well. So from spawn2 to pipes, typically this is found with post-exploitation. It'll be spawned off that spawn2 process. And so not every process generates pipes. And I bring this up because if you see a Mojo pipe occurring off of service host, it's most likely not Chrome. And so Mojo is like the Chrome kind of default here. And kind of the thing I missed on the previous slide on the pipes here is the hashtags for these with named pipes, it just random digits will show up. So it'll be mojo.random numbers. So it's the same for this. If you see any pipes coming off of non-browsers, if you see it coming off of Explorer, those things are going to be highly suspect. And that's sort of like the whole baseline your environment for understanding what's using pipes. So then our next one, this one's really interesting. I haven't seen much about this out there in the wild, but the compile time is really interesting, and this can be configured in the malleable profile. It's kind of like time stomping. You're basically saying my beacon payload, like say it's an executable, it's either it looks to be compiled back in 2009 at this time and whatnot. And so the range of this, people seem to modify it, and the range does, in my examples, you see people will put it in the future, they'll put it in the far past, whatever it may be. And I think it's interesting because a lot of EDR products or a lot of tools and the way they sort it in their UI, you might only see the latest binaries, but you're not going to see either the future binaries or the ones that happened way in the past until you start digging into it. Previously, the default was this one on the screen, 14 July 2009. But I'm not seeing that too much anymore. That seems to be really changed. For instance, Threat Express in their jQuery profiles uses the 11 November 2016 4832. That's default across all their profiles. All right, on to the watermark. Now, I'm not a threat intelligence analyst, but the watermark is meant to be unique for each customer and sometimes can be assigned or attributed to different threat actors out there. Depending on the blog you're reading, if it's about Cobalt Strike or ransomware group or something, you'll probably see a watermark tag that says, hey, we found this with them. This is attributed to TrickBot or Maze or this group. Hard part about it is, as you see on the right, the more leaked ones are probably going to be the ones with the more higher scores or more volume that we find out there when we're scanning. So like the watermark of 0 was a leaked version. And then previously I saw on a blog, like the Maze one right there, I don't know, can they spin up 400 team servers and use it? Probably, but there's most likely yet another leaked version that's being used and spread as well. So watermark's interesting, but I myself, again, I'm just kind of like Spider-Man point. It can go any direction. And when you start looking at it and try to attribute it, I wish I had the GIF actually working. Okay, DNS is really interesting. We started digging into this a while back here at Splunk because it's just a little bit different. You can obviously do DNS like beaconing or tunneling through a couple different tools out there, but Cobalt does it a little bit different because you can modify these settings in the profiles. Now we get the DNS idle from all the scanned and all the malleable profiles. And in this particular case, you can see the default is always quad 0. And generally, all of the other settings stay the same. I haven't really seen too many people or profiles that change these. And so reason why this quad 0 is important is because when a beacon is beaconing out over DNS, it will hit it'll hit the record, but the IP comes back as 0. So if you have a box just hitting 0 all the time, and then all of a sudden it gets an IP, it's probably suspect. And so this data is from that attack data that I shared earlier, a link to it. You can see the IP, 3 different IPs, and then it goes to 0 because now it's just waiting for something to do. So it's just checking in. And they changed these to Google IPs for the most part. So if you find run DLL32 hitting quad 0 or hitting quad 8, it's probably suspect and something else is going on in your environment. TXT records with it is extremely noisy. If you wanted to find a host that was beaconing with TXT, it'll be the only box in your environment hitting TXT records. It just does lots of traffic over and over. And then some examples of those URLs and how the API, CDN, and post, how they look. And again, and this is all within our attack data as well. All right, last is HTTP. I wanted to just show it because this is probably one of the more things, is definitely one of the parts that I don't write enough about, just because it's pretty static, but it's also hard to detect. So if you're looking at network side, you're going to only see someone hitting Amazon.com with a very specific URI of field keywords books. Do these change? No, they're very static. So maybe that's kind of the piece that when you look at an ET signature, you see those static values, and that's more than enough. I would say if you're seeing this off of a non-browser based process, this would probably stand out more than anything, but you have to correlate the process, right, with the network data and understand what's doing the what. So again, these are very, very, very much customizable, and you can stack multiples of these as well in a malleable profile. There is a lot of data here. I'll share all these links in our Slack channel so that you can click around and play with the help file and look at some other default settings and my notes as well.
Hey, I think both of us want to say thank you so much for coming. And again, we'll be in Slack, and huge shout out to Mike Kalara. I'm sorry I murdered your name. Shad Tilbury, IronNet, again, Wade Hickey, the DFR report, and many, many, many more.